on Grothendiecksia in the quasi-split unramified case. So please.
Thank you very much, and thanks a lot for the invitation to give a talk at the seminar. So I'd like to discuss the Grothendieck-Serre conjecture, which concerns reductive groups and their torsors. So let me begin my talk by just recalling what that conjecture is about, recalling its statement, and the cases, overviewing the cases in which it has been established so far, just giving some context. Okay, so it concerns reductive groups and their torsors. So just to make sure we're kind of on the same page, let me recall what a reductive group is over kind of an arbitrary base scheme, or maybe I'll just restrict to affine basis. It's really captures the everything that I need. So a reductive group over a ring R is a smooth affine R group scheme whose fibers are connected reductive groups. So it's a smooth affine R group G such that, whose fibers are connected reductive groups. And in other words, such that for every prime number P, for every prime P of this ring R, the base change of G to the geometric fiber of G at this at the corresponding point of the spec of R is a connected reductive group. It is connected, and the reductivity condition just means that it has no non-trivial no non-trivial normal subgroup that is unipotent, that is an iterated extension of the additive groups, that's an iterated extension of GAs. All right, and this is somehow the abstract definition, but we all know reductive groups. These are just kind of matrix groups with trivial unipotent radical, for instance, tori, GLN, SLN, PGLN, SON, spin groups, various exceptional groups. Anyway, so these are the kinds of groups that we're talking about, and the point is they make sense over any ring. They are defined. These split groups even defined over Z. Now we'll be talking about quasi-split reductive groups a lot. So let me just recall what that means. So a quasi-split group, reductive group, is roughly speaking, is a group that has a Borel subgroup, at least over semi-local base. That's what the definition amounts to. So for that, let me recall that a closed R subgroup B is a Borel subgroup if B is smooth and its geometric fibers are Borel subgroups. So in other words, again, for every prime ideal P in R, the base change of B to the algebraic closure of the corresponding residue field, that's a subgroup of the corresponding base change of the corresponding reductive group that's a geometric fiber of G, and this is a maximal connected solvable subgroup of maximal connected solvable subgroup. So that's what reductive groups. That's what a Borel subgroup is, and it just. In the case of GLN, for instance, Borel is one of the Borels is just upper triangular matrices, or lower triangular matrices in SLN. Same of PHLN. Somehow for a general reductive group, you embed it into GLN and intersect with the upper triangular matrices, and that's one example of a Borel. And the abstract definition is takes the form that I just gave. And in general, well, at least if R is semilocal, has only finitely many maximal ideals, then G is called quasi-split if it has a Borel subgroup. Quasi-split if it has a Borel R subgroup. And all these examples above are quasi-split. In fact, they're even split, which is somehow even better. Now, a fact of life as it pertains to reductive groups is that in fact the quotient of a reductive group by a Borel subgroup, I mean, both G is affine by assumption and B is a closed subgroup, so it's also affine. The quotient, however, is not affine, is proper over R, and so that's somehow how well, at least for the purpose of this talk, is an important thing to remember about Borel subgroups. So anyway, let's just get to the statement of the conjecture that we'll be discussing, the Grothendieck-Serre conjecture. So this came somehow through several iterations of more and more generality. First, it was proposed by Serre in a somewhat more restrictive setting that I'll discuss, and by Grothendieck, at least for PGLN, and then also Grothendieck speculated could hold for any, say, semi-simple group scheme, and then maybe even reductive group scheme. So anyway, the modern formulation of this Grothendieck-Serre conjecture says that if one has a regular local ring R, and so, for instance, a local ring of a smooth variety over a field, that was a kind of setting that Serre was imagining, at least, or maybe the field was even algebraically closed, but that doesn't matter too much for us. So for a regular local ring and a reductive group scheme over this ring, a reductive R group, G, one would like to consider torsors under G, principal homogeneous spaces equipped with IG action, and so smooth affine schemes over R equipped with IG action, such that locally they become isomorphic to G equipped with a G action. And one wonders, well, which of these homogeneous spaces trivialize, become isomorphic to just G equipped with its right translation action over the fraction field of R, and the conjecture is that in fact, if a torsor trivializes over a fraction field, then it must have been trivial to begin with. In other words, this map of pointed sets, torsors under G over R and torsors over a fraction field. Now, the corresponding pullback map is supposed to have trivial kernel. No non-trivial torsor trivializes over the fraction field. In other words. That's what Grothendieck-Serre conjectured, and the conjecture, I mean, they checked it in some cases, of course. That's why the conjecture was plausible. For instance, if for example, if the case when G is GLN. What the case when G is PGLN? Well, first of all, the case when G is GLN is trivial, right? Because if G is GLN, then torsor is the same thing as a vector bundle, and vector bundles over local rings are trivial. So even the H1 in the source of this map is trivial. So certainly the kernel is trivial as well. The less trivial cases, somehow less trivial cases, perhaps the case of PGLN. This is related to injectivity of the Brouwer on the level Brouwer groups. One has a Brouwer group of R and a Brouwer group of the fraction field of R, and because R is regular, Grothendieck proved in his Brouwer free paper that this pullback map on Brouwer groups is actually an injection, and well, the Brouwer group, it's second Étale cohomology of R of GM with torsion classes in there, and it receives it receives a map from torsors under PGLN, somehow connecting map coming from a central extension GLN modulo the central GN is just PGLN, and that connecting map that realizes this torsors under PGLN as a subset of H2 et al, because torsors under GLN actually are all trivial, as we just remarked, and because of this result of Grothendieck about the Barrow group, which somehow takes advantage of techniques in really abelian cohomology, then because GM is abelian coefficients, then we deduce that actually for PGLN, the map to the fraction field is then also injective. So we get this injectivity, which is just from this commutative diagram, and the result of Grothendieck, and this is somehow the case of PGLN, which perhaps the first non-trivial case of this conjecture that has been settled, and this was kind of an inspiration to make the conjecture for more general groups. Okay, so let me actually quickly overview the cases the cases of the conjecture that have been established since. After we've seen these somehow very basic ones. So first of all, already when G is a torus, but not necessarily a split torus, not necessarily a power of GM, but a general torus is not that obvious. In fact, it was settled by Collet-Hélène and Saint-Suc in 87. They used so-called Flask resolutions of tori. So some tori are better behaved with respect to these H1 properties over regular rings. For instance, if the torus is just induced torus from a finite et al cover, then again the H1s are trivial, as it was the case for GLN, and more generally, somehow if the torus is Flask, closely related to this induced tori, then again one can get a grip on these H1s, and a general torus has a resolution where can be somehow resolved in terms of these quasi-trivial and Flask tori. Okay, so this is a first kind of general case of the conjecture. That's when the group G is somehow as simple as possible, yet being non-trivial. The case when R is as simple as possible, yet non-trivial, is when R is a discrete valuation ring. So this case was done by Cesnavicius in 1984 in his Harvard PhD thesis. It heavily uses Brouhat-Titz theory, and also Hardar's work on approximation for reductive groups. Anyway, I won't really go into the argument because that's not the focus of the talk. Actually, Cesnavicius' argument kind of had some unclear points and some perhaps little gaps, which were explained by Ningguo a couple of years ago, who gave a presentation of Cesnavicius' argument in full. So the case when R is a discrete valuation ring, in fact, implies another case in which R is simpler. For instance, if our regular local ring R is Henselian, for instance, just complete, such as, rings of this form, for instance, power series just over ZP, just an example. So this case actually follows from the case when R is a DVR. The point is that when R is Henselian, then the triviality of a torsor over R, because of Hensel's lemma, it kind of amounts to a triviality of the induced torsor over the residue field. And so this I mean, so one does not need to work with all of R, but somehow just with the residue field, and one needs to interpolate between the residue field and the fraction field of R. And for that, one can kind of break R up into a chain of DVRs, like considering a chain of prime ideals. I mean, that is a fully saturated chain, and localizing and taking quotients, somehow playing around like that, one can reduce the case of the general conjecture to a case. In the case when R is Henselian, to the case of DVRs, which was settled by Cesnavicius. All right, so these are kind of the general results when either G is simple in some sense or R is simple in some sense. Now, the first kind of exhaustive result, which covers fairly, I mean, general class of R and general class of G, is due to Fedorov and Panin. Of course, there was a lot of prior work with slightly more restrictive hypotheses, but let me just say the other major case that is known is when R contains a field, when R is of equal characteristic. So this caught attention of many authors actually throughout the years, and there were number of cases established before Fedorov and Panin settled it in general in 2015. First, they were assuming that R contains an infinite field, and Panin removed that assumption and also allowed finite fields. And later, Fedorov actually gave a simplification of these arguments, which kind of then finite or infinite, that distinction does not matter so much. And in fact, the argument is also simpler than those previous works. Okay, and well, this case 4 maybe perhaps settles Serre's conjecture the way he phrased it, because he was only interested in varieties over a field. So that's, in fact, Serre's question was already covered by Kolyotelen and Ojanguren in the 1990s, and Fedorov and Panin built. I mean, that was really the first big result that popularized this kind of question and made people more aware of it. So other than that, there are some sporadic cases when G is specific or R is specific. Perhaps R is low dimensional, of dimension 2 or of dimension 3, and G is also specific, just like for PGLN. I mean, for some reason that case is simpler because one can relate to something else. There are some other cases like that, but I will not really go into surveying them here because they will not really play much of a role in what follows. So the case I would like to discuss is a mixed characteristic. Well, so the equal characteristic case of the conjecture is already known. We then focus on mixed characteristic, and in mixed characteristic, the simplest kind of regular rings are unramified ones. Well, in fact, the kind of so in mixed characteristic, a regular local ring is either unramified or ramified, and the unramified ones are the ones for which these kind of problems are generally, I mean, tractable, or at least more approachable, definitely, than for ramified rings. So we start with this case. A regular local ring is called unramified if either it's of equal characteristic, so if either R contains a field, but that's really not the case that we kind of have in mind, but formally speaking, that's also unramified. So if either R contains a field or R is of mixed characteristic, that means that its fraction field has characteristic 0 and the residue field has positive characteristic P, and that characteristic of the residue field is P, is it's in the maximal ideal, just because the residue field is, it has that characteristic, but it's not in the square of the maximal ideal. So for instance, let's just get some examples of what we're talking about. These unramified regular local rings could be just, you have this polynomial algebra over Z, you localize it at this ideal, or in fact, any local ring of a smooth of a smooth scheme any local ring of a smooth scheme over Z localized at P is an unramified regular local ring. If that point lies in the generic fiber, that's of equal characteristic. Otherwise, it's mixed characteristic regular local ring. Okay, so these are the class of rings that we will consider, and the theorem that I'd like to talk about is that the Grothendieck-Serre conjecture holds in the case when the regular local ring is unramified as defined in the sense that we just reviewed, and the group G is quasi-split. It has a Borel subgroup. For instance, G could be split. That case is already new. So okay, so the quasi-split unramified case. In other words, and just as a little bonus, let me mention that for such R, for unramified regular local rings R, a reductive R group H is split in the sense of being one of these very explicit matrix groups. Like there's a classification of split groups combinatorially, and the reductive groups like that are defined over Z. And anyway, okay, so these are the most simple kind of ones and untwisted somehow reductive group schemes. So a reductive R group scheme is split if and only if its generic fiber is split. Its base change to the fraction field is split. So so this property actually conjecturally should hold for any R, and any reductive group, not necessarily unramified R. And we can show it in this unramified case that if the generic fiber happens to be split, then in fact the group itself is split already. And well, this is related to the Grothendieck-Serre conjecture somehow, because isomorphism classes of reductive groups are classified by each one of the automorphisms of split reductive groups, and those are extensions of some locally constant, some constant group by adjoint group, and the study of torsors and the reductive groups then is very much relevant for this kind of question. Okay, let me just give a quick corollary to further illustrate this this theorem. By taking G to be various concrete groups, one arrives at concrete statements about the ring R and its arithmetic. So, for instance, by taking G to be orthogonal groups and actually doing a little bit more work, but not too much, we obtain the following corollary: that because we'll talk about orthogonal groups, so let's just assume for simplicity that 2 is a unit in R. So if this happens, then non-isomorphic, and of course R is unramified, as it says in the theorem, unramified regular. So and of residue characteristic which is either 0 or odd. Then non-isomorphic, non-degenerate quadratic forms over R cannot become isomorphic over the fraction field. Isomorphic over the fraction field of R. Similar statement to that about splitting of reductive groups. If something happens over a fraction field, then the thing happens also over R. Okay, in this case, the something is isomorphy of two given non-degenerate quadratic forms over R. So somehow, if for a fraction field you can find some change of variables that one quadratic form becomes the other, then those coefficients in the change of variables, of course, a priori involve coefficients in the fraction field, but a posteriori, due to this corollary, actually you could find perhaps another change of variables or something such that one quadratic form becomes the other already over R, and the coefficients are over R. That's roughly speaking what this corollary is saying. Okay, so let me just make a couple of quick remarks about what we use for the proof, and then I'll proceed to actually discussing outlining roughly how the proof of this theorem of this mixed characteristic Grothendieck-Serre conjecture case goes, roughly speaking. So first of all, what do we use from preceding results? So the proof uses known cases 1 and 2. So these were cases when either G is a torus, the Collet-Sansuk case, or when R is a DVR, the Cesnavicius case. So we will use those, but not the other ones. The Fedorov-Panin case in particular, we will make no use of it. So in a case when our unramified regular local rings happen to be of equal characteristic, then we'll just reprove that special case of the Fedorov-Panin result in equal characteristic. And well, another remark is that actually the same statement as in the theorem holds. In fact, so we prove a slightly more general result. So same statement holds when R, the ring R, regular ring R, is merely semi-local, not necessarily local, and still unramified. And still unramified. Okay, so somehow in these questions, sometimes it's better to consider the case when the ring is not only local but kind of also allowed semi-local regular R, because that somehow intervenes in intermediate reductions. Anyway, we'll do that. And also the unramified assumption could be replaced by being geometrically regular over a discrete valuation ring whose residue field is perfect. That's another technical improvement, so the statement of this main theorem is actually a little more general than what I put here, but this, in this case, is the simplest and already contains all the main ideas and avoids some of the technicalities. So let me proceed to discussing the steps that go into the proof. In fact, there are quite a few a priori different ideas that enter here and kind of mix well with each other. For instance, Artin's technique of good neighborhoods, notor normalization and mixed characteristic, theory of affine Grassmannian also is enters, and compactifications and of tori, of torsors under tori. I'll try to explain as much as I'll be able to in the time I have. So just to fix the setting and get started, let me assume let me fix the unramified regular local ring R that we have, and a reductive R group G, which we assume to be quasi-split, have a Borel subgroup, quasi-split, reductive R group G, a generically trivial G torsor, generically trivial G torsor E. So that's what we have for this main theorem. the Grothendieck-Serre conjecture says that any such E would in fact have to be trivial. So what we want is that E is trivial, torsor is trivial if and only if it has a section. In other words, that E has a rational point. That's what we want to prove. We know that E has a rational point over a fraction field. Okay, so just to get started, I would like to kind of highlight right away how the Borel subgroup, how the quasi-splitness helps. So I'll denote a Borel subgroup over R just by B, subgroup of G, and I'd like to begin the overview of the proof with the following claim, which is where the Borel subgroup enters and where we see how it simplifies the matters. I mean, in this particular question. So the claim is that in this setting of a reductive, I mean that we fixed the generically trivial G torsor E, in fact there is a closed subscheme Y of spec of R of codimension at least 2. Well, so E ought to be trivial. So E ought to be trivial over all of spec of R. But what we prove first is that there is a closed subset Y of kind of small of codimension at least 2 such that the restriction of E to the complement of this, well, we cannot prove right away that it's trivial as it would have to be, but at least we can prove that it reduces to a torsor under the unipotent radical of this Borel subgroup. So in the case, I mean, in the case of GLN, the Borel say is one Borel is upper triangular matrices, and unipotent radical is such matrices that have ones on a diagonal. And in a general reductive group, general Borel subgroup has the same kind of structure. There's a unipotent radical, which is, well, if you embed into GLN, just intersect with matrices with ones on diagonal, that's your unipotent radical, and then the quotient is a torus. So anyway, the restriction of E to this complement of Y, actually, we don't know right away that it's trivial, but at least we can prove that it reduces to this to a torsor under this unipotent group, under this solvable group. So let's see how this goes. So so first of all, well, E is smooth and affine, and B is smooth and affine, and we take the quotient of B acting on E. G acts on E on the right, and so B does too. And this quotient is proper because, well, basically because G mod B is. That was the fact about Borel subgroups that I recalled, and E is eta locally on R isomorphic to G. So E mod B is eta locally isomorphic to G mod B, and so by étale descent, E mod B is proper. So the valuative criterion. So the valuative criterion applied to this E mod B implies that there exists such Y such that this quotient has a point over the complement of Y. The torsor E generically is trivial. That's part of the assumption, and so E has a point over a fraction field of R. And by taking that point over a fraction field, that induces a point on E mod B, and we just use valuative criterion to spread it out uniquely to a point of E mod B over all height 1 primes, and we get this spread out, and it misses some closed subset of codimension at least 2. Okay, so what this means, the points of this quotient of E by B, they parameterize reductions of the E torsor to B torsor. So E restricted to spec R minus Y reduces to a B torsor. Okay, in fact, we want a reduction to a unipotent radical of B, but that's a start. At least we know that it reduces to this large soluble group. Now let T be the quotient torus, Borel modulo unipotent radical of the Borel, so that, that's a torus. And for tori, there's a purity for torsors under tori due to Collet-Hélène and Saint-Sucre, who studied torsors under tori over regular basis. Anyway, what this purity tells us is that this, so I'll call that a B torsor EB. And if I take a quotient of EB by the unipotent radical, I get a torsor under the torus T, and this torsor extends. It's defined away from a closed subset of codimension at least 2, and by purity for torsors under tori, on a regular basis, it extends to a T torsor. To a T torsor over all of spec R. So we can get rid of this. We can get rid of this Y for torsors under tori, but then and in fact even to a generically trivial T torsor, because E was generically trivial and somehow we inherit that the unique extension to a T torsor of this quotient inherits that property, and because. So by Grothendieck-Serre for tori, the generic triviality implies actual triviality. If we have a torsor under torus of a regular local ring, and it's generically trivial, then Collet-Hélène and Saint-Sucre says that case of Grothendieck-Serre is already known. The torsor must be trivial, and so what we get is actually that this induced torsor under T is trivial, because we can extend first to a general trivial torsor over R, and then use Grothendieck-Serre to a known case of Grothendieck-Serre to conclude it's trivial. And so this must actually be trivial also over this complement of Y. In other words, this must have a section. And what that means is that B torsor that we had, that E reduced to, in fact, it even further reduces to an RUB torsor, because when we quotient on the right by the unipotent radical, that we have a section. Okay, so that's a claim, and now let's let's just warm up somehow, but that shows how the Borel subgroup is relevant for this relative criterion of properness. And so let's proceed to discussing somehow the main portion of the proof while having this claim in mind. So the main case of the result that I'd like to talk about is when I said that I will allow R to be of equal characteristic as well, but just for purposes of exposition, let's just focus on the main new case, namely when R is of mixed characteristic 0p, so that we can so that it's more concrete what we're talking about, really. So okay, the main difficulty in this conjecture is that we cannot somehow enlarge R, because for instance, we cannot just pass to the Henselization or completion of R for free, because then the conjecture is already known. And any such enlargement of R somehow can trivialize torsors a priori, and we're not allowed to do that. The only kind of simplifications that we can do on R is shrinking it, somehow making it smaller or larger. And so just as an example, the first technique really that enters into this is Popescu approximation. Popescu approximation says that in fact any regular local ring that is unramified, it's a filtered direct limit. R is a filtered direct limit of localizations of smooth ZP algebras, localizations of smooth Z localized at P algebras. In other words, that case of unramified regular local ring, which was just local ring at a smooth Z localized at P algebra, in fact, is somehow not as specific as one would think a priori. So because there's Popescu, theorem of Popescu, which, okay, is a special case of more general statement. Actually, anyway, so then by using a limit argument without loss of generality, R is then the local ring of mixed characteristic of a smooth Z localized at P algebra of a smooth affine Z localized at P scheme X of relative dimension D, and I assume positive relative dimension right away, because if relative dimension D is 0, then X is actually a DVR, and I mean, then R is actually a DVR, and that case is already known. So we'll just focus on this. Okay, so and then G, E, and Y, all of these objects are somehow defined over spec R a priori, but they spread out, of course, to a neighborhood of spec R in a smooth affine scheme whose some local ring is R. So, and by shrinking X, I can assume that these spread out to groups, to a group, to a torsor, to a closed subscheme over all of, or defined over all of X. Okay, so that's some further preparations. And let's get started on the actual overviewing the actual proof. So the first step is Noether normalization in quotation marks, because Noether normalization usually happens when you have varieties over a field. Here we're in mixed characteristic. Nevertheless, we'll see that there is a statement of the sort that we can use. In fact, okay, so first of all, Noether normalization, which says that if you have a finite type d-dimensional algebra over a field, say, then it admits then it has a finite morphism from the polynomial algebra in D variables. In other words, spec of R admits a finite map to the affine space. That's not normalization over a field. This does not hold in mixed characteristic, because somehow you could have quasi-finite algebras over Z localized at P, say, which have different cardinality, or I mean, well, which are not finite. Over Z localized at P, and so even this relative dimension 0 situation, Noether normalization does not hold. Nevertheless, we find a version that suits for us, and so the version of Noether normalization that we argue is that there is an affine open U inside X, which contains spec R, contains that local ring that we're really interested in for studying E, and the map pi smooth of relative dimension 1. Okay, so there's a fibration into curves whose base S is an open inside the affine space. So affine open S containing, just for sake normalization, containing the 0 section. So Noether normalization naively would say that there exists somehow a finite map from X to the affine space of dimension D. Here we drop D by D minus 1, and we find a fibration into curves like that, such that, moreover, some finiteness property is still retained, namely the intersection of Y with U is, so Y was of codimension at least 2, and this is actually finite, literally finite over S. So we find this kind of presentation. We find this fibration to curves that such that y, that small closed subset, which eventually we want to eliminate, that closed subset is actually finite over this open in the affine space. Okay, so that tells us that our a priori arbitrary smooth Z localized at P algebra affine scheme X admits a pretty specific form in the end. Let me just quickly mention what are the main ingredients in this step. This step is quite geometric. It uses Bertini theorems, first of all. Well, these are relevant, especially in the case one, to handle some subtleties about finite residue fields. Anyway, one uses Bertini theorem applied to some smooth, projective compactification of X, not necessarily smooth, and one uses techniques from Artin's construction of good neighborhoods. This is material from SJ4. This was over a field, algebraically closed field, and this was used to show that the tau cohomology with the QL coefficients agrees with. Is compatible with the usual Betti cohomology over complex numbers. Say that compatibility isomorphism, that was kind of the engine behind this result, and we rework this theorem in mixed characteristic and find a version that we can use to find this neutral normalization, to find this preparation fibration into curves. And there were earlier versions of this kind of presentation, Lamau due to Quillen, who used it to study algebraic K theory. This was again over a field, and due to Gaber also over a field. These were in the setting of studying K theory and Gersten conjecture for K theory. Okay, so that's that for step one. So we have this nice presentation. Let's proceed to step two, which really is pretty formal and it's just a reformulation really. So now that we have this fibration, let's try to use it, and let's use it as follows. So let me just draw what we have. We have our affine space of relative dimension 1 less, and we have our open S. In fact, okay, so S is an open in the affine space, and over S we have a fibration into curves, into smooth curves, and the zero section is an S, and we also have Y, which pure maybe not okay. So we have a Y, which is finite over this S, and our spec R that we kind of are really interested in is some local ring here in the total space. So that's our spec R, and all our group G and the torsor E all live over this total space that is now called U. It's an open in the old X. We have this fibration. Okay, so what we will do is so spec R of course maps to S, because spec R is just a local ring in a total space. So certainly it maps to S, but we will take kind of a new copy of that map like that, and we'll just base change this whole picture. So we get some C over R. So what do we get actually if we do this base change? Just for free, for properties of the map U goes to S, properties of that map pi, we get that C over R is a smooth affine R curve. And okay, because it comes equipped to the section delta, right? Because our spec R occurred in the total space here, and we just took another copy of spec R. So certainly there's a map from spec R back to the total space, and so that gives rise to this section delta. So we have a distinguished section delta, and we have by base by base changing z, by base changing y, sorry, script y, we have here, we have z, a closed subscheme. So z over c, as c inside c is an R finite closed subscheme. Okay, so that's all just geometry, but what about the group that we're really interested in and that we'd like to study? So over U, we have our script G, the reductive group. And if we base change that script G to C, well, we get the reductive group over C. So G over C is a quasi-split reductive C group scheme, reductive C group with Borel subgroup, I mean, with some Borel subgroup B, base change over Borel, corresponding Borel of over U. And this pair is such that the pullback under delta of this inclusion of Borel is actually just our old Borel inside G that we know and love and that we started from. This is basically because, I mean, because our group G need not come from S itself, when we do this base change, it somehow, the script G over C, it need not come from spec R and somehow non-constant group over C with the Borel a priori. But at least when we pull back across along this delta, it is just the old B inside G. So there's that compatibility. Okay, and likewise for a torsor, E over C is a G torsor, G torsor over C. Okay, so it's a G torsor such that delta pullback of E is just our torsor that we wish to study, I mean, in the first place, and E, due to that claim and how this was all set up, E reduces to a torsor under the unipotent radical of B on the complement of C. Right, but by the claim, we had that the Y was chosen in such a way that that our torsor reduced to a torsor on the unipotent radical away from Y, and that was kind of spread out to X and then inherited by U, and then after base change, this property is then inherited by this E, and that's the interaction of the R finiteness of Z and this I mean, E away from Z is not, we don't know a priori that it's trivial, but at least it reduces to torsor under unipotent radical of a Borel on this complement. Okay, so that's what we have, and it might seem like nothing much happened with just base change, but the upshot is that now we have the flexibility of changing C somehow. I mean, now we can do kind of some geometric manipulation, some arguments, some more presentation lemmas or something to really simplify this picture. We have all this data, and yeah, so we will in the next steps we kind of eventual goal is to reduce to C being just A1, very simple smooth affine curve over R, and then conclude the triviality of E, which is a pullback of that script E by using affine Grassmannians. Affine Grassmannians are relevant because they parameterize somehow the ways, in the case of A1, they parameterize the ways in which our torsor E could be extended to torsor on the projective line. Okay, so well, there are kind of a few more steps, and I don't have so much time to really go into much detail, but let me just tell you at least what they are. So first of all, the next step is to equate G, the script G, to make it constant. I mean, and the base change of the group G to C itself. So the idea there is that if we take that section delta and we Henselize along delta, if we Henselize C along delta, one can actually prove that if one has a Henselian pair, then a reductive group scheme subisomorphism over the ring and over the ring modulo ideal, where in that Henselian pair, these are in bijection. These isomorphism classes, at least if our modai is geometrically unibranch, for instance, normal. Anyway, so this does not quite suffice because we want to retain the finiteness of this Z over R. Well, we prove some finer statement than that, allowing us to change this C, replace it by some finite that I'll cover at least after shrinking along Z, and so that then eventually we were able to simplify our script G to just base change of G, and this uses compactifications of torsors under tori. Compactifications of torsors under that torus T that we saw, and this maybe happens over. Yeah, the point is that these compactifications are not only over a field, and so we use toric geometry in a relative setting to construct them. Okay, this step 4 is to replace C by the affine line. Once we kind of repaired our script G, we can repair C somehow. So this uses using excision and certain presentation lemma, which again in the spirit of Quillen and Gaber. Basically, we want a map from C to A1, a quasi-finite map, to build such a quasi-finite map, which, because C is regular, it will automatically be flat by the miracle flatness theorem, well, really just Buchsbaum, also under Buchsbaum, and such that Z would map isomorphically to some Z prime closed subscheme, and in fact, such that this diagram would even be Cartesian, at least after shrinking C suitably. And this is kind of presentation lemma one can do. I mean, one can do, and then one can use excision to kind of glue patch up torsors to replace C by A1. And finally, the final step is use affine Grassmannians to study the torsor E over A1 of R and show that the delta, which now without loss of generality becomes a zero section, that this is actually trivial, knowing that our E is trivial away from this our finite closed subscheme Z. And let me just finish by saying what is the key geometric fact that is used here about affine Grassmannians. So the key fact is that if we have, okay, so we have our affine Grassmannian of G, and we could look at its connected component of the somehow neutral section. Then we can look at the derived subgroup of G, and it's simply connected cover. Just by functoriality, we get this map F, and this is always surjective on field valued points. That's somehow geometric input that we use. And just for context, I will recall that if the characteristic of the field in question, I mean, does not divide the cardinality of the central isogeny involved, namely of the pi1 of the derived subgroup of G, then this F is even an isomorphism. Even an isomorphism onto the reduced associated reduced closed sub in the scheme of the affine-Grassmannian. And in general, it need not be an isomorphism, but at least field valued points lift even in those bad characteristics. And we use this to proceed. In fact, if G is split, a lot of these steps simplify significantly, but for quasi-split G, these are the inputs that help us. And I'll stop with this. Thank you.
Yeah. Thank you very much. Any question or comments?
So how about this assumption G is quasi-split? So in the general case, this approach does not work.
Sorry, could you repeat?
So you assume that G is quasi-split.
Yes.
You mentioned it. So, but in general case, yeah, this approach does not work.
Yeah, so in general, if G is not quasi-split, then basically I don't have this claim. My torsor E is still generically trivial, of course, just by assumption, and so it is trivial away from some Y, which is of codimension at least 1 then. But I do not get of codimension at least 2 for free somehow. Okay, something then happens away from codimension 1. And then that lack of codimension at least 2 is actually a problem in later geometric steps. Like the main bottleneck is, I guess, in this neutron normalization. To prove this, I actually use that Y is of codimension at least 2 in U, say, that in this intersection. The key is to get this finiteness over S. And if Y is just of codimension at least 1, the way this Newton normalization proof works is we embed X into some X bar, which is projective and flat over C localized at P, and then we also take the closure of Y, and that closure of Y, its intersection with the new fibril components in X bar could be too large to kind of eliminate them by cutting by hypersurfaces in the Artin's good neighborhoods technique. So somehow, yeah, there's some technical problem in this step that where I need that Y be of codimension at least 2, and it's not clear to me whether there really isn't any way to modify somehow and to get around that difficulty, but so far it seems pretty subtle. Okay. In fact, before I had a version of this theorem for just for split G, and going from split to quasi-split also was a little subtle, but it turns out that this technique somehow can be used at least to capture that case. But I don't know how to go beyond quasi-split actually.
Okay, thank you.
The assumption that the DVR is unramified is to utilize the Popescu theorem, right? Or why?
Yes, it uses Popescu theorem. And that assumption is yeah.
Yeah, and in the general case, you think it is true or you think it is wrong or any proof? I mean, without the
you mean the Grothendieck-Serre conjecture?
Without the assumption.
The Grothendieck-Serre.
Yeah.
The Grothendieck-Serre conjecture should certainly be true. In that case, it's just that there's very few geometric techniques about how to go about, attacking it in that case. And in fact, for many related questions, there's a conjecture of Bass and Quillen, which says that if you have a regular local ring and you have an affine line over that, and every vector bundle over the affine line is actually trivial. So that conjecture is kind of a flagship kind of problem in the spirit, and that is the open case is also ramified mixed, ramified regular local ring. So that ramified case is really the most difficult one in all of these questions, and it's just not so many techniques. I mean, basically not any techniques how to really approach that, because we cannot really enlarge R. So somehow we cannot just pass to completion and use some structure theorem of coend
So
or something.
you cannot. Yeah. You cannot enlarge it in terms of regular ring, right? But you can have kind of irregular limit of some non-regular ring, or I don't know.
Yeah, in fact, Popescu has proved recently that any regular ring, ramified, for instance, is a filter direct limit of a regular, but essentially a finite type over Z. So there is some reduction to something more geometric over Z, but then later, I mean, in this particular argument, I do use quite significantly that my X is actually smooth over Z localized that be not just regular, not just some stable degeneration or something like that. It really is smooth. And so not so clear how to proceed there.
I see. Okay. Yeah. Yeah. Any other questions or comments?
I have a question, okay? So, may I have a question regarding the step 1? Is there any special method to specify the affine open U, or is it easy to find such an U? Such that the Y intersection U is finite over U, affine open S.
So in practice, this U is first we embed X into some X bar, which is projective and flat, and U is a complement. Is a complement of some hypersurface. I mean, intersected with X, but it's not. I don't really know how to control that hypersurface. Really, yeah, the idea is that we have, let's just imagine that X is projective for simplicity. Then we cut X by transverse hypersurfaces iteratively, by hypersurface and by another transverse hypersurface, so on, so on, so on, so on, maybe d-1 times. And the equations of these hypersurfaces give this map pi. Like the coordinates of the affine space, they get mapped to the defining equations of the hypersurfaces. And the vanishing locus of the hypersurfaces is then the preimage of the zero section under this map pi. And this U is just a complement of a hypersurface. And the way Y becomes finite is that we cut by sufficient. I mean, we cut so that by d-1 hypersurface such that Y becomes the intersection of Y with those hypersurfaces is finite over Z localized at P, and then we just spread out in the neighborhood of zero. So it's a bit inexplicit, but I don't really know how to. I mean, for instance, if one starts with an any X affine and smooth, and one wants this map pi defined on all of X, I don't really know how to do that, how to get this neutral normalization without shrinking somehow.
Oh, so you mean to exclude some kind of exceptional set to get the euro?
Yes.
To avoid the criticality.
Yeah, I don't know.
Okay. Yeah, thank you.
Okay. So I think let's thank the speaker for a very interesting talk.